Our today's lesson plan is multiplication rule of probability. So by the end of the section, we will be able to explain independent and dependent events, solve problems using multiplication rule, and recognize the difference between sampling with replacement and sampling without replacement. Approximate probabilities for dependent events. So we'll start with definition. Two events, E and F, are independent if the occurrence of the event E in the probability experiment does not affect the probability of the event F. Two events are dependent if the occurrence of the event E in the probability experiment affects the probability of the event F. The rule for understanding the independence is called product rule or multiplication rule. A and B are independent if probability of A intersection B is probability of A times probability of B. And you can extend it for any number of events. The multiplication rule for n independent events says probability of A, B, C, and so on in intersection is going to be the probability of A times probability of B times probability of C, and so on. In sampling with replacement, the randomly selected unit is returned to the population after being selected, when the sampling without replacement is and sampling where the event selected is not returned to the original sample space. So when a sampling with replacement of successive draws can be considered as independent event, the sampling without replacement has to be considered as a dependent event. So just think about a situation. If you are selecting an item, checking the item and putting it back in the original sample, then the probability of drawing the same item the second time doesn't depend on the probability of drawing the item in the first time, because you have replaced the item, so it is an independent event. Whereas if you have drawn an item, did not return it, then the sample space is actually missing that item now. So drawing the same item one more time is going to be changed depending on whether you have drawn this item in the first draw or not. So this has made drawing without replacement a dependent event. So independency and dependency are very closely associated with drawing with or without replacement. If you are drawing with replacement, then it's independent. If you are drawing without replacement, then it is dependent. The 1% guideline says, suppose successive draws such as those for a random sample are being made from a population. If the sample size is no larger than 1% of the size of the population, then the probability of the dependent successive draws from the population may be approximated using the assumption that the draws are independent. So what does it say? If the number of things we are selecting is less than 1% of the entire population, then without loss of generality, we can think of the process of selection as an independent process of selection. Irrespective of whether we are doing the selection with or without replacement, we can calculate the probability assuming that it is an independent probability event. So we're going to explore the dependency a little bit, and we will do a bunch of exercises. So let's start with our first exercise, and this one is EPT pregnancy tests. The packaging of an EPT pregnancy test states that the test is 99% accurate at detecting typical pregnancy hormone levels. Assume that the probability that a test will correctly identify a pregnancy is 0.99, and that 12 randomly selected pregnant women with typical hormone levels are each given the test. What is the probability that all 12 tests will be positive? So I want each of these 12 tests to be positive. So what I want you to understand is the first person, the test result being positive, has no implication with the test result being positive or negative for the second person, and so on. So each of these tests becoming positive or negative are independent events. So in some ways we can say you want to find the probability that the first person has tested positive and the second person has tested positive and the third person has tested positive and so on. You wanted all 12 of them to be tested positive. And see how I'm writing the 12 tests. P for positive and the subscript 1, 2, 3, 4, 12 are which test I'm talking about. So I want all of them positive. We talked about this event being independent. So this probability is simply going to be probability of P1 times probability of P2 times probability of P3 times probability of P12. Each of these probabilities are 0.99 and I have 12 of them. So I'm multiplying all of them, which is equivalent of writing 0.99 whole to the power 12. So I'm going to find this number, round it to 4 decimal places. So let's do 0.99 and I'm going to raise this number to the power 12. So 0.99 to the power 12. Let me get all the symbols by, and then I do to the power 12. So this number rounded to 4 decimal places is going to be 0.8864. And the next question is asking me, what is the probability that at least one test will not be positive? So at least one test will not be positive means what? At least one test will be negative. Let's think about it first. That means one can say one test is negative, or 2 tests out of the 12 given are negative, 3 tests out of the 12 given are negative, and I can carry on till I reach 12 tests, all of them are negative. And these are all the situation that is covered under saying at least one test is negative. At least one means it can be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so that is all the situation that is being covered under the umbrella of at least one test is negative. What are the other possibilities in this testing? 1 test is negative, 2 tests is negative, 3 tests are negative. What is the situation that I did not write on the board? Well, all the tests are positive. That is what I did not write. Why I wanted to do this? For you to understand, you know the probability of this thing already. And now you want to know the probability of this thing. So what do? Use the complementation rule. You say that probability of the required event, which is at least one test is negative, is equal to probability of all positive complement, which is what? Which is by the formula 1 minus probability of all positive. And I know this number, so I will say that this is 1 minus 0.8864, and that's going to be 0.1136. That answers your question. So basically, looking at the term at least, it has triggered me to think the problem in a little different way. I could have done finding the probability of 1 test being negative, 2 tests being negative, 3 tests being negative, and doing all the 12 cases and adding them up. Instead, I thought about, well, what is the other thing that is not covered by saying at least 1 test is negative? The only thing that it did not cover by saying at least 1 test is negative is no test is negative. That means all tests are positive. And I already found the probability in the previous part for all tests are positive. So subtract that probability from 1 and you get your required probability. Answers your question. So we'll go ahead and look at our next problem. This is about cold streaks and hot streaks in baseball. Cold streaks players in sports are said to have hot streaks and cold streaks. For example, a batter in baseball might be considered to be in a slump or a cold streak if he has made 10 outs in 10 consecutive at-bats. Suppose that a hitter successfully reaches the base 30% of the time he comes to the plate. Find and interpret the probability that the hitter makes 10 outs in 10 consecutive bats, assuming that at-bats are independent events. So it has told me that at-bats are independent events. Also, it has told me the hitter makes an out 70% of the time. So you want 10 outs at 10 bats. So write it in this way: probability out the first time, out the second time, out the third time, and out the 10th time. All of them are outs. So this is just going to be probability of out 1 times probability of the second time out, and probability of out in the 10th time, because this is independent event as we are given. Each of these probabilities is 0.7. And I have 10 of them, so I will do 0.7 to the power 10 to find the probability. So let's see how much is that. So we'll say 0.7, and then we're going to raise it to the power 10, and we'll get rounded to 4 decimal places. Answer is 0.0282. So this is 0.0282. Change it to percentage for answering the next question. So probability wise, we're done. We're done with the first question. Then the next question is, are cold streaks unusual? So what I do, I change the probability to percentages. So that is going to be 2.82%, which is way less than 25%. So we said that, yes, these are unusual. So in probability, we say that an event is unusual if the probability of the event is less than 25%. So since the probability of being in cold streak is way less than 25%, we will say that this is unusual. Find the probability that the hitter makes 5 consecutive outs and then reaches base safely. So now you want to know probability of out in the first one, out in the second one, out in the third one, and I'm writing union, so they should all be intersections because and out in the second one. So intersection out in the second one, out in the third one, out in the fourth one, out in the fifth one, but the sixth one is not out. And see how I have written it. Not out, so I said complement of out. These are all independent events, so you will say probability of O1 times probability of O2 times probability of O3 times probability of O4 times probability of O5 times probability of O6 complement. Well, each of the first 5 probabilities are 0.7, so I will say 0.7 to the power 5, and the last one should be 0.3. Because probability of being out is 0.7, so probability of not being out is 0.3. Let's find this number. We'll do 0.7, and then we will do to the power 5 times 0.3, rounded to 4 decimal places is 0.0504. So that answers my question. The next problem is asking us about hot streaks. In a recent basketball game, a player who makes 65% of his free throws made 8 consecutive free throws. Assuming that free throws shots are independent, to determine whether this feat was unusual. So I want to know the probability of being able to make a free throw is 65%. This player had made 8 consecutive free throws. So F1 intersection F2 intersection F8, which being independent is the product of the probabilities. I have 8 of them. Each time the probability is 0.65. So it's 0.65 to the power 8. You want to know this number and check whether this is unusual. So we'll do 0.65. And I'm going to raise it to the power 8. Round to 4 decimal places, I will get 0.0319. And this is approximately 3.19%. Again, you see this is way less than 25%. Hence, this is unusual. And that is really simple, and we have answered this question. We go to our next problem. This is about acceptance of sampling. You are in charge of purchasing for a large computer retailer. Your wholesaler delivers computers to you in batches of 100. You either accept or reject the entire batch based on a random sample of 2 computers. If both computers you sample are defective, then you reject the entire batch. Suppose that there are 10 defective computers in the batch of 100 computers. Should you conduct your sampling with or without replacement? So how many you are selecting? You are selecting 2 out of 100. So that is 2 over 100, so equal to 2%, and that's more than 1%. So according to the 1% guideline, because my sample size is more than 1%, I have to do this selection. It cannot be independent. So I have to select without replacement. And that means it is a dependent selection, so we should be a little careful. Cannot directly multiply everything. Okay, question number 2. What is the probability that the first computer you select is defective? Remember, there are 10 defective computers. I say probability that the first one is defective, so I'm using D for defective. First computer is defective, it is going to be 10 out of 100. So that's 1 over 10. Second one, what is the probability that the second computer you select is defective given that the first one is defective if you sample without replacement? So I want to know probability that the second one is defective given that the first one is defective. So remember what happens here, I cannot multiply directly, so I have to think it separately. How do I think it separately? We will say probability that the first one is defective is 10 out of 100 because there were 10 defective computers. Now you have selected the first one defective. So now there are 9 defective computers. And there are a total of 99 computers because my selection is without replacement. So it will be 9 out of 99. So I get 1 out of 10 times 1 out of 11, and that's 1 out of 110. And that's the probability. D. What is the probability that you will accept this batch? So you are going to accept this batch unless both computers are defective. And I know the probability when both computers are defective. This is the probability when both computers are defective. So probability of accepting the batch is everything other than both computers are defective. So I will say that this is 1 minus 1 out of 110, which is 109 over 110. So probability of accepting the batch is 109 out of 110. What is the probability that you will reject the batch? Well, that's exactly C. So I will say probability of rejection is when both computers are defective, and that's C. So that's 1 out of 110. And that answered my question. So we'll carry on to problem number 4 about 9/11 information. Within 2 weeks of the terrorist attacks of September 11 in 2001, the Pew Internet and American Life Project conducted a survey asking, among other things, from which medium the respondent received most of his or her information regarding these events. The results indicated 1.9% of Americans received most of their information about September 11 from the internet. Assuming independence, find the following probabilities. So we are assuming independence to start with. Number 8, 2 randomly selected people both received most of their information from internet. So receiving information from internet, I'm going to call it I. So probability, first one received their information from internet, second one received their information from internet. So that is going to be probability of I1 times probability of I2. Again, remember these are done independent way, so I'm using multiplication rule. Probability of receiving most of the information from internet is 1.9%. So that's 0.019 in probability times 0.019. So this is going to be 0.000361. That's the probability. Then the second one, 2 randomly selected people both received most of their information from sources other than internet. So now you want the first one to receive most of their information from sources other than internet. So I use internet's complement, and the second one is the same way. And again, don't forget this is independent, so I can write it as probability of the first one receiving most of their information from sources other than internet times probability of the second one receiving most of their information from sources other than internet. If receiving information from internet is 0.19, then not receiving it from internet is 0.981 for both of them, and I multiply them. So this is a little difficult to multiply, so I will use my calculator and I will do 0.981 times 0.981. Round to 4 decimal places, I will get 0.9624. So this is 0.9624. Third one, 5 randomly selected people received most of their information from sources other than internet. So the same problem, but I do it for 5 times. So probability of I1 complement intersection I2 complement intersection I3 complement intersection I4 complement intersection I5 complement. And that is product of I1 complement because of the independence times probability of I2 complement times till I get probability of I5 complement. Each of them are 0.981 and I have 5 of them, so I do 0.981 to the power 5, and I'm going to do that number in calculator as well, round to 4 decimal places. So 0.981 to the power 5 rounded to 4 decimal places is 0.9085, and that is the answer. We carry on to the next part of this problem. Part D is saying at least one of 3 randomly selected people received most information from the internet. At least one of 3 randomly selected. So how do you write it? Again, think in this way. At least one of 3. That means what? It means 1 of 3, 2 of 3, or all 3 of 3. All of this situation is under at least 1 of 3. So what is not been written yet? 0 of 3 received from. So this question asks you that at least 1 of 3 randomly selected people received information from internet. So I'll say 0 of 3 received from sources other than internet. And we find this probability. So we say probability that no one of 3 received information from sources other than internet, or actually you should have said sources. Let me clarify this thing one more time. So the question asked me to find the probability of at least 1 of 3 received information from internet. So I'm interested in understanding that. So what I said, 1 of 3 from internet, 2 of 3 from internet, 3 of 3 from internet. So what it didn't talk about, 0 of 3 received their information from internet. That's what I'm trying to find out instead, which is probability 3 of 3 received their information from sources other than internet. And I know these are independent events, so I will write it as probability of internet 1 complement, internet 2 complement, and internet 3 complement. So that should be probability of I1 complement times probability of I2 complement times probability of I3 complement. Each of them are 0.981. I have 3 of them, so 0.981 to the power 3. And we're going to find this number round to 4 decimal places. 0.981 to the power 3. So rounding to 4 decimal places, it will be 0.9441. But remember, this is not what we are asked. This is the probability that no one received their information out of these 3 people from internet. But I want to know at least one, so I want to know the complement. So I will say probability of the required, which is at least one received from internet, will be 1 minus probability of no one, which is 0.9441, and that is going to be 0.0559. And that answers my question. And we will go to our next problem. Treasury bonds. One of the most important tasks for economists is to make forecasts for the performance up or down of investments such as 30-year treasury bonds. The Journal of Investing, Volume 6, Number 2, page 88, 1997 reports that in a sample of 36-month surveys, the consensus estimate of performance for the 30-year treasury bond has been wrong 20 out of 30 times. So it has been wrong 20 out of 30 times. Find the probability that 2 randomly selected consensus estimates were correct. So 20 out of 30 is probability of wrong. So that's 2 over 3. I want the probability of being correct, so that will be 1 minus 2/3, that's 1/3. The next question, are we doing it with replacement or without replacement? For the first question, remember you were selecting 2. So 2 out of 30 is 2 over 30 times 100. So this is going to be 6.67%, which is more than 1%. So according to the 1% guideline, we should do the selection without replacement. For the first one. And I want both of them to be correct, so probability of correct in the first one and correct in the second one. So for the first one, you have 10 of them are correct out of 30. But once you have selected the first one correct, there are only 9 of them left correct out of 29. So that answers in 3 over 29 as your final answer to the probability. The second one is asking, find the probability that 3 randomly selected census estimates were wrong. So for the same reason, because 3 out of 30 is 10%. More than 1%. The 1% guideline will say that selection must be done without replacement. We will cross it that way. And we will say probability. This time I want all of them to be wrong. All 3 of them. So the first time you are selecting the wrong, it is 20 out of 30. The second time you are selecting the wrong, one has been selected, so 19 out of 29, and then you have 18 out of 28. And I can simplify this thing. So first and foremost, I will get 2 over 3 times 19 over 29, and then I will get, if I divide both top and bottom of 18 and 28 by 2, I get 9 out of 14. Then the 3 cancels the 9, and I'm going to get, and 2 cancels 7, the 14 and gives you 7. So it's 19 times 3 over 29 times 7. So 19 times 3 is 57, and 29 times 7 will be 7 times 9 is 63. So 6 carries on, 7 times 2 is 14, plus 6 is 200. So 57 over 203 is my answer, my final probability. So let's see what is in C. Question number C is asking me, if we choose 2 consensus estimates and if we sample with replacement now, find the probability that the second consensus estimate was right given that the first one was right. So now you want both of them to be right, but you are selecting with replacement. So the probabilities are independent. So this is C1 times probability of C2, and that's going to be, the first one is 10 out of 30, or 1/3 times 1/3, which is 1/9. The fourth one, so in this part it is also asking, are the successive draws independent? Why or why not? So I'm going to say that yes, they are independent. And why not? Why they are independent? Because you have done as selection wise with replacement. Remember, with replacement doesn't have any effect on the probability of multiple draws, so it is independent. Okay, we'll carry on to number 4. Question number D. Repeat C, this time sampling without replacement. We did it already in part A. So this time probability of C1 intersection C2. Again, remember, 10 of them are good the first time you draw, and then 9 of them are good, so you get 3 over 29. And finally, it is asking you, are the successive draws independent? Why or why not? So we'll say that no, they're not independent. As we have drawn without replacement. And that completes the answer to this question, and we will go on to answer our last question. An aerospace company has submitted bids on 2 separate federal government defense contracts. The company president believes that there is a 35% probability of winning the first contract. If they win the first contract, the probability of winning the second contract is 66%. However, if they lose the first contract, the president thinks the probability of winning the second contract decreases to 53%. What is the probability that they win both contracts? So I'm asking to find out what is the probability that win in the first one and win in the second one. This is what we are trying to understand for the first one. So remember, the company president believes that there is a 35% probability of winning the first contract. If they win the first contract, the probability of winning the second one is 66%. So these are clearly not independent events. So the first one is 35%, so it's 0.35. But winning the first one, winning the second one is 66%, so this is 0.66. And that is going to give me the probability for the first one. So we're going to calculate this thing. So 0.35 times 0.66 is 0.231. Answers your first question. What is the probability that they lose both contracts? So probability of losing the first one and losing the second one. So if they have a 35% probability of winning the first one, then their probability of losing the first one should be 65%. But in that situation, what is the probability of losing the second one? So first, I want you to understand the probability of losing the first one is 65%, so 0.65. Now remember, if they lose the first contract, winning the second one is 53%. So if they lose the first one, winning the second one is 53, means losing the first one and losing the second one is 47%. So this time you're going to multiply 0.47. So we're going to go get 0.65 times 0.47. So this is 0.3055. And our final question is, what is the probability that they will win only one contract? And that can happen in two ways. Probability they win the first one and lose the second one, plus probability of they lose the first one and win the second one. Again, remember, winning the first one, the probability is 0.35. Winning the first one and winning the second one is 66%. So winning the first one and losing the second one should be the complement of that, which is 34%. So I will say this one is 0.34 plus losing the first one, the probability is 0.65. And in that situation, winning the second one is 53%. So that's 0.52. So this is the number that we're going to calculate. So let's do that. We have 0.35 times 0.34. And then we have plus 0.65 times 0.53. And that should be 0.4635. And that answers my question. And that is going to conclude our study of mutual independence of events and multiplication rule as well.